Hi, this is Mark Weitzman. Welcome back to my YouTube channel, Theoretical Physics with Mark Weitzman. Today I want to do a video on a problem in Srednicki's book, problem 10.5. This is part of lesson 10, and this is a very instructive problem. Let me make this a little bit bigger so you can read it better, maybe. Okay, so the problem is that the scattering amplitude should be unchanged if we make a field redefinition. Suppose, for example, we have this Lagrangian and we make the field redefinition. Phi goes to phi plus lambda phi squared. Work out the Lagrangian in terms of the redefined field and the corresponding Feynman amplitude rules. Compute at tree level the phi goes to phi scattering. You should get 0 because this is a free field theory in disguise. Okay, so let's work this out. Okay, this is problem 10.5. This is going to be part A. I think I'll do this in 2 parts, although I'm not sure how long the video will be. We'll see how it goes. We have the Lagrangian. This is problem 10.5 in Srednicki. And it's on field redefinition. Lagrangian, we have a free field Lagrangian, our standard scalar free field Lagrangian. I'll just call this free field theory, scalar. And our field redefinition is phi goes to phi plus lambda phi squared. And we need to work out the redefined field theory. So our problem is work out the new Lagrangian. And the corresponding Feynman rules. Then we have to, so this will be like what part A is on, and part B will be compute at the tree level the phi goes to phi scattering amplitude. Now this problem is it's not particularly hard, nor is it easy, but I do remember getting a sense of accomplishment when I worked this out about 17 years ago. If you can do this problem, then it gives you a pretty good indication that you've understood the first 10 chapters of Srednicki's book. So it's kind of like you use a lot of different things. Anyway, let's first start with since we have phi goes to phi plus lambda phi squared. Let's just work out what partial mu phi goes to the partial of mu phi plus lambda, the partial of mu phi squared. Let me just correct something in my notes. Um, okay, and this is equal to the partial mu phi plus 2 lambda phi partial mu phi. Okay. So now we just substitute in the Lagrangian. L goes to L prime is equal to minus 1/2 partial mu phi plus 2 lambda phi partial mu phi. Now we do the lower part. Minus 1/2 m squared phi plus lambda phi squared. And we'll expand this out. You have to be very careful with your calculations in this problem because you want to get a final result of 0, and if you make a mistake at any point in time, you're not going to get 0. So it's one of those problems you do have to calculate carefully. Now we rearrange this so we take out what the free part of the new Lagrangian is. So this part over here is just L0 prime, the free part of the new Lagrangian. Now we get a lot of what we call derivative interactions, which you often don't see in beginning quantum field theory. I remember when I first learned field theory from Borkin and Drell, you didn't really see it until you did scalar electrodynamics. That was the first theory that had derivative interactions, and you have to treat them carefully. So these terms are the new Lagrangian prime, the interaction part. Okay, now I'm going to do something which you don't have to do, but I'm going to integrate by parts the derivative terms in the interaction Lagrangian. And I'm doing it just because I sort of know how to handle it a little better. But you can't get rid of the derivatives altogether, but you can make it where you get a nabla, del squared, rather than just a single derivative. Rather than having two derivative terms, you'll just have the Laplacian or the D'Alberton squared acting on it. So let's just do that. So let's take the term minus 2 lambda phi partial mu phi partial mu phi. Now when we integrate by parts, we never worry about boundary terms when we're students in quantum field theory. Maybe later, but not now. And so we change the sign to lambda. I take the derivative from the last term and I put it on the first two terms. Then I have phi when I take it off that. And this is equal to 2 lambda partial mu phi partial mu phi. And it looks like we're not making any progress because we seem to get the same term here as we had when we started. The sign is different, but it doesn't seem like we made any progress. But it will help us because now we get 2 lambda phi squared. Now we have the partial squared. Remember, I'm just going to write down here. Partial squared is equal to the partial mu. So I have that opting on phi. So I'm just a little bit more comfortable. Now I can solve, so this implies that 4 lambda phi partial mu phi is equal to minus 2 lambda phi squared del squared phi. And so the advantage here is that here I had 2 terms with derivatives in it. Now I only have 1 term with derivative in it, but it's a second order derivative. And so this implies that minus 2 lambda phi partial mu phi is equal to lambda, just dividing by minus 2 here, lambda phi squared partial squared phi. So that's one of our derivative terms. Now I'm going to do the same thing with the other derivative term. Minus 2 lambda squared phi squared partial mu phi. This is equal to 2 lambda squared partial mu phi squared partial mu phi, and then phi again. And this is equal to 4 lambda squared phi squared partial mu phi plus 2 lambda squared phi cubed partial squared phi. So this implies that 6 lambda squared phi squared partial mu phi is equal to minus 2 lambda squared phi cubed partial squared phi. And now we just divide by minus 3, minus 2 lambda squared phi squared partial mu phi is equal to 2/3 minus 2 is equal to 2/3 lambda squared phi cubed partial squared phi. Okay, so now we have L prime is equal to L prime interaction lambda phi squared partial squared phi plus 2/3 lambda squared phi cubed partial squared phi minus lambda m squared phi cubed minus 1/2 lambda squared m squared phi to the 4th. Okay. Now I have to get the Feynman rules. For each of these terms. And I'm mostly going to do this with hand waving. The book sort of has worked it out for a bunch of these, and you can follow the same standard method either through the path integral or through the canonical correlation functions formula that it gives in the interaction derivation in the previous chapter on one of the problems. So I'm just going to assume that you're up to date. And let's do the first one. Minus 1/2 m squared lambda squared phi to the fourth. Here's the interaction. And we know that we represent this by minus 12I m squared lambda squared. Basically, whenever we have just a polynomial, we're going to end up getting just the constants in front of it, except that if it's like 3, we'll have 3 factorial. Here it's 4, we'll have 4 factorial for reorderings. 4 factorial is 24. 24 times a half is 12. So, and we always put an I in there when we do it, because when we expand an exponential, it's like e to the I times the Lagrangian. So I just put it as minus 1/2 I times 4 factorial. And this is lambda squared. Okay. Now, for the next one, we have a 3-point function, a tree with a 3-point function, minus lambda m squared phi cubed. And here it's, it's the same thing, minus 6I m squared lambda. We put the I in there, and we take 3 factorial, which is 6. Okay. Now we have 2/3 lambda squared phi cubed partial squared phi. This is going to be acting on a diagram like this. Let's say K1, K2, K3, K4. Okay, and I'm going to put a heavy dot here. This is a heavy dot means that it's a derivative interaction. Okay. Derivative interaction. And so this is going to be, I'll write it down, minus I times 4 lambda squared K1 squared plus K2 squared plus K3 squared plus K4 squared. So where does this come from? You can look at problem 10.4 to see how you get these things. I just like to think of it as when we have a partial squared in position space, it goes to a minus k squared in momentum space. And then we can, it can act on any one of these momentum that are incoming. That's why we get K1 squared plus K2 squared plus K3 squared plus K4 squared. We like to, when we do these interactions, we like them, all the momentum to be incoming and sum to 0. But not when they're internal. But anyway, so that's where we get the K's. And the other factor we get is, well, first of all, we have the 2/3 lambda squared to start with. And then we don't have any factor for the, even though this can occur at 4 spots, we've taken that into account by having different K's at each spot. But we still have the remaining 3 fields. We have 3 factorial reorderings that we can do there times 6. We always multiply by the I. Actually, we multiply by a minus I. When we when you derive this, okay, the k squareds give you negative. When I where did I write that down? Sorry. In momentum space, we get a minus k squared. So that gives me a minus sign in front of all that. Then we multiply by the I. And then we have 2/3 lambda squared. And then 3 times, I'll just write 3 factorial for the fields. So it's 6 times 2/3, which is 4. So we get minus 4i lambda squared. Okay. Next term will be the same way. Lambda phi squared, partial squared on phi. Now we have three fields. Remember, this partial squared is acting twice, but it's only acting on one field. So now we have k1, k2, k3. And so now it's minus 2i lambda k1 squared plus k2 squared plus k3 squared. And again, it's the same thing. The partial squared gives you a minus sign with the k's, each one squared. And then we always multiply by I, minus I lambda. And now we have 2 factorial. Okay, but anyway, let me put a box around this for a 3-point vertex, and a box around this for a 4-point vertex. Okay, so I think I'll do this in one video and I'll finish it. It's not that hard. So now we're going to do part B. Let's get the tree scattering amplitude. Phi goes to phi. So what we have is we have 4 external legs. First thing is to combine. When I first did this problem 17 years ago, I didn't combine the full point amplitude. So I had a lot of diagrams with, starting with this one over here, and then I went to the next one, and I didn't combine the 4 and the 3s, and it became algebraically very messy. It worked out in the end, but I've grown up a little bit. Now I'm 69 years old, and I'm getting a little bit I'm smarter and tireder. So let's do the 4-point scattering, and this is equal to minus 12i m squared lambda squared minus, we just add up what we had, the 2 diagrams that we had calculated before, minus 4i lambda squared k1 squared plus k2 squared plus k3 squared plus k4 squared. Okay. Now we can rewrite this as let's just see how we write this. First of all, I want to write in here minus 4i lambda squared. I want everything. I'm going to add an m squared 4 times. K1 squared plus m squared plus k2 squared plus m squared plus k3 squared plus m squared plus k4 squared plus m squared. So altogether I added minus 16i m squared lambda squared. So I added that on this side, so I need to add 16i. So I have minus 12 plus 16 I m lambda squared. So this is just equal to 4i m squared lambda squared minus 4i lambda squared times k1 squared plus m squared plus k2 squared plus m squared. This will save a lot of work if you don't do this. Okay, so this is the 4-point, I'll call this IT 4-point tree. Now let's work out the okay. I've sorry, there's more I can do with that. But each of the at least for what we're doing, each of the KI for the 4-point is on shell. Remember, that means that KI squared equals minus M squared, or KI squared plus M squared equals 0. So all of this is 0 basically. So now we have the scattering 4-point tree is just equal to 4I M squared lambda squared. That was the sort of the simplification that I had missed years ago. Okay, so now let's combine the this will be a little bit more difficult, but it will work out pretty well. Combine the 3-point vertices. So the total three-point vertex factor is minus 6I M squared lambda minus 2I lambda K1 squared plus K2 squared plus K3 squared. So here we have K1, K2, K3. Okay, now this is very easy to work with, because here I'm just going to write this as minus 2I lambda K1 squared plus M squared plus K2 squared plus M squared plus K3 squared plus M squared. Now in this case, the K's aren't all equal to 0. So we're going to use these 3-point vertices to make a 4-point tree diagram. So we get the 3 diagrams of figure, which I'll write them down. Figure 10.2 representing the S, T, U channels. And so we have, this is the S channel. Srednicki uses primes. I'm just going to number them 1 to 4. Now, I said before that we have all the momentum incoming, but it doesn't matter, because even if I were to write this as minus K1 plus K2, when I square it for the amplitude, I'm just going to get the same thing, so it doesn't matter. So this is the S channel tree diagram. Then I have This is the T channel. It's not going to show up. And the hard one to draw is always the U channel. Okay. So for each 3-point vertex, two of the external lines represent momentum that are on shell, and the internal line is off shell. So now we get the 3-point tree contribution to the scattering amplitude is, so using what we developed earlier, I have minus 2I lambda. Then I'm going to have, like in the S channel, this one over here, and this one over here, these are external, and the internal is there, so I'm going to get when I add, let me just make sure I go back to my 3-point thing. So when it's on shell, it doesn't contribute. Like two of them might be, if K1 and K2 are on shell, then this and this will be 0, and the other one won't be 0. So I'm going to get minus 2I lambda. And K3 in that thing, let me go back to the diagram, is now K1 plus K2. That was what was K3 before when I showed the 3-point diagram. So now I get K1 plus K2 squared plus M squared. Then I have the propagator, which also happens to be the same thing. And that's why everything cancels here. Plus M squared. And then I have the vertex on the other side, which is the exact same thing. Minus 2I lambda. K1 plus K2 squared plus M squared. So this is the S channel. And I'll write out, but I'm not going to explain it anymore, but the T channel works, and the U channel work the same way. Now I have K1 minus K3 squared plus M squared minus I over the propagator. T channel, and then the U channel, U channel. Okay, so now if you add them all up, you're going to get 4I lambda squared K1 plus K2 squared plus K1 minus K3 squared plus K1 minus K4 squared plus 3m squared. Now, in particle physics and in the next chapter in Srednicki, we make the usual definitions for two particle going to two particle scattering. These are the Mandelstrom variables. You don't have to do this, but it just makes it a little prettier. And because we're using a certain metric, we have minus signs here. Another typo here. So in terms of these variables, we get IT tree 3 point. It's actually 3.2 goes to 2 scattering. It's not really the 3 point anymore. This is equal to 4I lambda squared minus S minus T minus U plus 3m squared. And it's easy to show. You can do it either through momentum and energy conservation, or I'm sure you've done it in particle physics, that S plus T plus U is equal to 4m squared. So when I substitute that in, I get 4I lambda squared times minus 4m squared plus 3m squared, which is equal to 4I lambda squared m squared. And then if we go back, what we calculated a minute or two ago, remember the IT tree 4 point. This was just equal to 4I m squared lambda squared. So the total transition amplitude tree phi goes to phi is equal to, it's a minus sign here. Let me make sure I got that typo fixed. Okay, it's equal to minus 4I lambda squared m squared plus 4I lambda squared m squared, which is equal to 0. So that's what we wanted to show. It's a nice result showing how field redefinitions don't affect anything. And means you have to be careful. If you look at a Lagrangian, it might seem complicated, but it might be. This happens when we do like spontaneous symmetry breaking and everything. It might be a relatively simple and symmetric Lagrangian, and then we do some symmetry breaking and it becomes very complicated. So you can't just look at a complicated Lagrangian and say, oh, that must be hard to work with. It may be a simple free field theory like this one was. Anyway, thank you for watching. I'll see you next time. Have a good day.